Okay, and welcome to Reactivity series to the extreme. What are we doing today, Mr. Walker?
We are going to be doing, as you said, reactivity series of metals. But it's not the normal metals. Normally we would use copper, iron, possibly magnesium, but they're all not that exciting. Magnesium is probably the best out of those usual metals. We're going to go for the really reactive ones, and they're at the top of group 1 of the periodic table. The metals are going to be lithium, sodium and potassium, but you can't get a good view of them because at the moment they're stored under oil. The reason for that is they're so reactive they will react with the moisture in the atmosphere if we leave them out, and they might even set on fire on their own in my store cupboard, which I don't want. So we've stored them under oil. Now I'm going to take them out of oil. I'm going to cut a tiny bit off and we're going to put them into water, and you'll get to see what happens with those 3 metals. So what should we start with, sir? The most reactive or the least?
I think start least, build our way up.
Makes sense. Like it. Best till last. So I'm going to get out the lithium. In fact, let's bring the camera in a little bit because you quite like this. Can you see there? The lithium is actually floating on the surface of the oil. It's the least dense metal you will find. So undense, that's not the right word. What would the right word be? The least dense. Let's just say it's so undense, don't ever say that yourselves, people, that it floats on top of water. Any other metal will sink to the bottom, so it's the lightest one. I'm going to get out quite a big chunk, but we're not going to put this size chunk into the water. Now I'm going to be very careful not to touch it with my fingers because it will react with the water that naturally is in the oils in my hand. So I'm going to chop a little bit off. It is quite soft. You wouldn't think it would be this soft. I can cut it a bit like hard cheese. And we've now got a nice surface there. Any ideas, sir, why that surface is so shiny when it kind of looks a little bit purpley and dull?
Is it something to do with the rest of the surface reacting in some way, shape or form?
Exactly that. Even though it's stored under oil, it does oxidise. So you're seeing lithium oxide on the surface of that. That's actually what lithium looks like. It's a nice silver metal. Well, silvery metal. It's weird though, because we could say silver is lithium-y, but we don't. We say everything is silvery just because we discovered silver first. So every other metal is silvery. But there you go. What we do need to do, I think I can put that size in, but I'm going to be ultra safe and just cut it up a little bit more. Okay. Now we've got a couple of pieces we can put in. I'm going to close that container just for safety. I'm going to move this back behind the plastic shield so there's no chance of any water splashing onto the bits I've got there. And come a little bit closer and we'll have a look when I put it in. Now this is not the most exciting one, but it does get better than that. As you can see, you wouldn't expect metal to do that when it touches water, but it does. It reacts and it releases hydrogen, which we're going to prove to you later. And it does seem to completely disappear. What's happened is it's reacted with the water and it's formed the metal hydroxide in the water, which in this case would be
lithium hydroxide.
Lithium
there we go.
Hydroxide. Look at that. Great bit of chemistry. So we've got lithium hydroxide in there, appearing to be gone, but it's actually in there. And we've also got hydrogen gas that's come off and it's just dissipated.
So I'm guessing our water's no longer neutral. We've lost that neutrality there because we've added an alkaline, is that correct?
Absolutely right. And we can prove that. We're going to prove that a little bit later on. We'll put the rest in, and then we've got the universal indicator out, which you can use later.
Brilliant.
And of course it will change colour. So what I'm going to do is I'm going to do it again with lithium, but this time we are going to try and light the gas that comes off. And as we light the hydrogen, we're going to see that we don't just light the hydrogen, we light the metal as well, and we get the colourful flame that we always get with the metal coming off the top. So the hydrogen will help it to stay alight, but the colour of the flame will be the colour that this particular metal always gives. So Sir's going to light the matches there, he's going to get ready. Okay. Once I put it in, because it's not as reactive as the other ones, it is safe to go in and actually light the gas. We might get a little pop as the hydrogen sets on fire and we'll see the colour of the flame. Here we go. Ooh, we've managed it.
There we go.
We have managed it. It got stuck on the side and we've got a nice red flame there from lithium. We heard a couple of pops, that was the hydrogen. So what we're going to do is this again, but we're going to change something about it. We're not actually going to try and light the metal, we're going to capture the hydrogen and then do the squeaky pop test, which you can see in a previous video. But this is done in a slightly different context. So Sir's got his collection device ready.
Nifty little contraption.
Here we go.
Oh, it's bubbling away there, sir.
It is indeed. Now hydrogen's lighter than air, remember, so it's going to go up into the boiling tube. And when it's completely reacted, which I think it has.
Yep, can't see the metal anymore,
Yeah.
sir.
We should have enough hydrogen in the boiling tube to be able to light it and get a nice squeaky pop. This is the test for hydrogen gas. If you're not sure what gas you've made, you can do this and see if it's hydrogen.
Right, I'll get ready to light it.
Here we go. The most difficult bit, lighting the spoon.
Lighting the spoon.
Always is.
Never thought it would take that long. Okay, let's have a go. Ooh.
There we go, we got a bit of a pop, not
Bit of
quite
a
a
pop.
squeaky one,
Bit of
but
a pop.
that was an okay one. That was an okay. A bigger piece would have made more hydrogen. Now what I'm going to do is put the lithium back inside. We have finished our experiments with lithium. We'll move on to sodium and we'll just try and light sodium. We won't do all the other business. And then we'll go on to potassium.
I think one of the reasons you said as well, sir, was the fact that because they're a bit more reactive, trying to catch the gas might be a bit more of a problem than it was for lithium.
Indeed it might be.
So, safety in mind here.
Now this piece, I've actually stuck it with my tweezers. Looks a little bit like a rubber and it's as soft as a rubber. It is incredibly soft. You wouldn't think so. You wouldn't think that was a metal. Looks more like a bit of plastic, doesn't it? But again, I can chop it down the side very easily and we get that nice shiny surface because we've got rid of the oxide layer. Over time, in fact, even within a few minutes, it would start to look like that. So let's put sodium in. The pieces have to be a little bit smaller officially, and they're going to be in reality because we have to be more safe because they're more reactive. So here is sodium. Let's have a look at that. Now that is definitely more reactive than the first one, isn't it, Sir?
It's one little sphere going around. I love how it darts around in the water as if it's living.
You're right, and well observed about the sphere. You see it's bouncing on the top of the water, it's reacting with the water, and it won't actually sink because it's so reactive. And that bouncing around knocks the edges off, so it makes it a sphere. Lithium wasn't reactive enough to knock the edges off, but this one is.
Look at it.
Zooms around like that. Now I'm just going to prepare another one, and this time Sir is going to light the gas coming off, which again is hydrogen. We could prove it with the hydrogen test, but we're not going to prove it this time. We're just going to tell you because it's true. He's going to light the gas, and we're going to see what colour flame we get with sodium. Sometimes it even lights itself if it gets stuck in a certain point. Here we go, Sir. Excellent, straight away it lit. It's now a nice little flaming ball, or it was a flaming ball of sodium going across the surface of the water. Well, while that's finishing off, I'm going to get what I think is the best one. It's my favourite. And there's hardly any potassium left in this because everybody loves it so much, they always do this one loads of times. So, here is the potassium coming out. It looks very, very similar to all the others. And if I chop it, we should be able to see that chops really easily and nicely.
That lithium, the lithium-y colour, is that right?
Yeah, the lithium-y colour.
colour.
Potassium is lithium-y. It's also sodium-y as well, coincidentally. We've got a nice shiny surface there. I'm going to have to chop that one in half just to be ultra safe because it is the most reactive. So as we go down group 1 on the periodic table, the reactivity increases. We could go further, we could go to rubidium and cesium, but they are super reactive and we can't do that in school, they're so reactive. I'd love to though. Are you
Might
ready?
not have a lab room anymore.
Yeah. It set fire to itself, it's so reactive. That was pretty quick, that one. We're going to do that
That was
again.
fast.
This is why there's hardly any potassium, because everyone goes, do it again, do it again. Here we go.
you hear that pop from the hydrogen straight away.
Absolutely.
And it always just explodes at the end there.
It did. The reason it explodes is because there's so much heat generated that as it gets smaller, it's too small to hold itself together anymore, so it blows itself apart. It will happen with a large lump if you put enough in, which we won't do, but with a small lump it usually does explode like that. And as you saw, we didn't need to light it, did we? It already
not
lit
at all.
on its own. We are going to have to do it twice more because it is so spectacular. Here we go.
Oh, another sphere. Oh,
That was a nice one. That burnt onto
splatted
the
on the
side.
edge there.
I like
Brilliant.
that. It's always slightly different every time, which I like.
Ooh,
Fantastic.
it's like fireworks.
Exactly like fireworks. In fact, metals like these could be used in fireworks to get the colours you see in the sky. Very often they use barium for green, strontium for red, magnesium for white. They don't often use these ones, but as you can see, all metals give off colours. So this is exactly where they got the idea from for fireworks. Someone did it and they went, let's send it up in a tube in the sky, set it on fire up there. And it works quite well. You mentioned the pH. So what should we do about that?
Oh, well, I think we have some universal indicator here, so I'm going to just add a few drops, see if the colour, we'd expect green if it was neutral, just a reminder there, red if it was acidic, blue if we're moving towards an alkaline. So
Yeah.
let's just add a few drops in. Ooh,
That is an interesting colour.
that is an interesting colour.
I'm going to mix it up
Mix
a
it
little
up.
bit. Put a few more drops
I will,
in. Should we
I
do
will.
that? That's it. That is quite a dark blue colour, I would say. Which means on the pH scale it's above 7. It's probably getting towards 10 or 11 because we've made not just lithium hydroxide, we made sodium hydroxide and potassium hydroxide, and they're all mixed up in the water together. So when we add universal indicator, we get this nice purple colour. Just to prove it, sir, see that plastic beaker there? Grab some water out of the sink and we'll just show you, just to compare the colours, what it would look like, what it did look like beforehand when it was water. So this nice greeny colour, that is pH 7, that's neutral, and we've definitely got a distinct blue colour. So we've raised the pH and we've made it nice and alkaline. Loads of different things we can do in that experiment, so I hope you enjoyed that quite long in the lab. Bye for now.
See you later.